Okay, so this is what we learned last time, right? So we define series. Series is basically a summation of real numbers, right? Which are indexed by natural numbers, right? And then, so obviously from series, you can generate a sequence that is a sequence of partial sums, right? So for a fixed n, you sum up all the terms in the series, right, up to that n term, then obviously that it creates a sequence, S1, S2, S3. So S1 is the first term, S2 is the sum of first and second term, S3 is the third term, sum of first, second, and third term, and so on, right? So in that way, you can generate a sequence. And then we see that to make sure the series is convergent, what we do is we just look at the sequence and we look at the convergence of the sequence, right? If it converges to a finite limit, then we say that the series converges, right? So that is what we saw last time, and obviously divergent also. We see that if the sequence converges to plus or minus infinity, then we say that the series is divergent, right? So eventually, what we do is we reduce the series, or we transform the series into a sequence and then look for the convergence of the sequence in order to see the convergence of the series, right? So it's the same for divergent as well, right? So that is what we did last time, and that is what we usually do with the series, right? In A level, you just write down the sum directly by using some kind of a formulation, and then you take the limit, and that is how you see sequence in A levels, series in A levels. But here, because we already studied about sequences, we look at series in terms of sequence, right? So then, so sequence convergence, you see a lot of important results, right? So especially the Koshi criterion also is an important criterion for the convergence of the sequence, right? So if the sequence is Koshi, then we say that the series converges, right? So that is what we see in the sequence. So we are going to develop such kind of results for series, right? So by using the results we have studied in sequences, we are going to develop similar type of results in series as well. So I'm going to prove one by one in theorems, right? Okay, so the first of those results is about the infinite term of the series, the last term of the series, right? So if the series is convergent, right? So if the series converges, then we can prove that the last term, right, of the series will converge to zero, right? The last term in the summation will converge to zero. So in order to prove this, we just use the properties of the sequences, right? So first, obviously, you define the partial sum. Right? So this is your partial sum, right? So then, when you know this, right? So then the partial sum Sn minus 1 is sum of all terms except un. Sn you have un also, right? So when you subtract, you will get un. So from this, you know un is Sn minus 1. So you have a formula for un in terms of the sequence, right? So un is basically Sn minus 1, right? So then clearly you know, right? So this you all know, right? If Sn is a sequence converges to a limit L, then Sn minus 1 will also converges to the same limit, right? So there is not much difference there, right? So that is one of the limit properties we studied at the beginning of the second chapter, right? So then clearly, you can see that limit of un is basically limit of Sn minus 1. But again, by properties of limit, you can write it as limit of Sn minus 1, right? So then clearly you can see that it is 0. So limit of un is 0. Right? So now what you have is, if the series converges, then the un term will goes to 0 as n goes to infinity. So the converse of that, right? So the contrapositive of that, you must have learned about contrapositive in your chapter 1, the chapter 1 of the other pure mathematics. When you talk about logic, right? Implies, you must have talked about contrapositive, right? So I'm going to write the contrapositive directly here as a remark. Okay. So now the contrapositive, if this does not hold, then the other does not hold, right? So P implies Q is equivalent to not Q implies not P, right? So you must have studied in your other pure mathematics, right? P implies Q is logically equivalent to not Q implies not P, right? So this implies this. So the logical equivalent is not of un goes to 0, that is un does not goes to 0, implies not of sigma un converges. So that is clearly sigma un diverges. So if you want to verify whether the sequence is divergent or not, right? One way is to look at the limit of the sequence Sn, right? Or you can just look at the last term un and make it goes to, and you can just take the limit of that, right? So let me give you an example of that. All right, so okay, so you have to show these two are divergent, right? So I will show the first one. Second one is quite easy, right? Because you know the partial sum, right? So that's not a big thing. But n sine 1 upon n, I will show you by using this result, right? So you know that. Okay. So you know that un is n sine 1 upon n. So that you can write it as sine 1 upon n over 1 upon n, right? So when you take limit of n goes to infinity, un is limit of this, right? So this is basically equivalent to this, right? So if you take x is equal to 1 upon n, right? Then when n goes to infinity, x goes to 0, right? So that is clear. If you take x is equal to 1 upon n, you know that when n goes to infinity, x goes to 0. And then limit of x goes to 0, sine 1 upon n is sine x divided by 1 upon n is x. So this from A level, you know the results, right? This limit, you clearly know it is equal to 1, right? This is equal to 1. And it is very obvious that it cannot be 0, right? So clearly, the sequence is divergent according to this remark, right? So this is one way of showing that a series is divergent by just looking at the last term, right? So the difference between the last two n and n minus 1 partial sums, right? So that's one way of doing, right? So now what we are going to do is we are going to look for the Koshi condition for the series. Okay, so we are going to look for the Koshi condition for series. You know this, right? So you know there exists n capital N of for every epsilon positive. There exists capital N belongs to natural number such that Sn minus Sm is less than epsilon for all m comma n greater than n. This is Cauchy condition for the sequence, right? So you all know we studied in second chapter, right? The Cauchy condition for the sequence Sn is for all epsilon greater than 0, there exists n belongs to natural number such that Sn minus Sm is less than epsilon, right? So now you can see that what is this, right? So this is clearly, right? So this, you know, this is summation of k is equal to 1 to n Sn minus k is equal to 1 to m s, sorry, sk, sk it's less than epsilon, right? So you know that. So you know that m and n are m and n are two numbers, natural numbers. So you can take n larger than m, right? So I'm going to take n is larger than m. So this subtraction you can write it as summation of k is equal to m plus 1 over n, m plus 1 to n, right? Sk is less than epsilon, right? So because this is this, right? So sorry, uk, sorry, these are uk's, no? So Sn, you know, is u1 plus u2 plus all the way up to um plus plus 1 plus all the way up to un, but Sm is u1 plus u2 plus all the way up to um only. So when you subtract, right, Sn minus Sm, right, so you get um plus 1, plus 2 up to. So that is how you write the Cauchy condition for the series, right? So by using this Cauchy condition, we are going to write the convergence results associated with the Cauchy criterion. So that we will write as a theorem again. Okay, so if you assume m is greater than n, then you have this as the Cauchy condition, right? So criterion. So then, so this is about the convergence of the sequence, right? So we have seen the results for sequence in chapter 2. Now we are going to do it for series, right? So now you see that Cauchy condition of this sequence is basically equivalent to Cauchy condition of this series, right? So that is clear, right? So then I will match with this notation. So let me change this a little bit. So n plus 1 up to n, or n greater than n. So now you see that, right? So Cauchy condition of this sequence is equivalent to this, right? So that is what we wrote here, right? Convergence of series is equivalent to the Cauchy condition of the sequence. Right? So I can write the proof now. This is theorem. I can write the proof. So you know, So you assume that summation of un converges, right? So if this converges, you know this is if and only if Sn is equal to k is equal to 1 to n uk converges, right? So you know that the sequence converges, right? Right? So the sequence is basically convergent, right? So then you know the sequence is Koshi. So you can write the definition. Okay. So here you see that, and so the sequence is Cauchy. If the series is convergent, then the sequence is convergent. If sequence is convergent, then by what you study in chapter 2, it is Cauchy. If it is Cauchy, this is the definition for Cauchy, or this is the way you write Cauchy sequence. And this modulus of Sn minus Sm is basically equivalent to modulus of k running from m plus 1 to n uk. Right? So then that is true. And if this one is true, then this one is true, this one is true, then Sn is Cauchy. Then Sn is Cauchy, then Sn converges. And if Sn converges, then clearly the series converges. So that's again by using the results we have in series, a sequence, we develop a Cauchy criterion for the convergent series as well. So now again, if the series is not Cauchy, right? So then you can prove that the sequence is divergent as well, right? So there are two ways to do it now. Okay, so now what I'm going to do is I'm going to show that summation of 1 upon n is a divergent sequence, right? So 1, 2, 3, 1, 1 upon 2, 1 upon 3, and so on is a divergent sequence. So now if I want to show it is a divergent sequence, then I need to show this condition does not hold, right? Right. So then and suppose the sequence is Cauchy. So then right, so then summation of 1 upon k is less than 1/4, right, for all m greater than n, sorry, n greater than m greater than n. And so that's basically right? So clearly you can take small n as capital 2 times capital N, and small m as capital N plus 1, right? Because m must be greater than n, so n plus 1 is greater, and n must be greater than both m and capital N, so you can always take 2n, right? So then you have a summation. And so then this is basically 1 upon n plus 1 plus 1 upon n plus 2 plus so up to plus 1 upon 2n is less than 1/4, right? So this is basically 1 upon 2n plus 1 upon 2n plus all the way up to 1 upon 2n is less than 1/4. Similar kind of exercise we did in the sequence as well, so that is why I am not explaining too much, because you know 1 upon n plus 1 is larger than 1 upon 2n, 1 upon n plus 2 is larger than 1 upon 2n, and here 1 upon 2n is equal to 1 upon 2n. So if this sum is less than 1/4, this summation of 2 1 upon 2n 1 upon 2n 1 upon 2n is also less than 2n. But there are n terms here, right? So what you have is n times 1 upon 2n is less than 1/4, and obviously that is a contradiction. You know, half is less than 1/4 is a contradiction. So it cannot be Koshi. If it cannot be Koshi, then it is divergent. And so this is how you show, or you use the Koshi criterion to show convergent as well as divergent, right? So if the sequence is convergent, then it is Koshi, the series is Koshi, and if the series is Koshi, then it is convergent. Similar to the results what we have in sequence, right? So now what we are going to do is we are going to see another convergent results which we see in sequence, right? So that is monotone convergence theorem, right? So we talk about limit first, and then now we talk about Koshi, right? So another results we see in sequence is monotone convergence theorem. So now we are going to see how we can implement that monotone convergence into the convergent of series, right? So that another theorem we are going to prove. So now you can see the proof becomes simple because it is just using the results of what we learned in chapter 2, right? So otherwise proving these results might take long, but because we already proved everything in chapter 2, we are just recalling them. So this is the theorem related to monotone convergence.
කැම් 4ට දාන්න ඒක න ගාන නැහැ මේ මැද කැම් එක කොහමද අයින් තියෙන්නේ එහෙම
Okay, so what you have is, right, so in sequence you know that if the sequence is monotone, then it is convergent if and only if it is bounded, right? So we see that in sequence, right? So here we are going to do that with a series. So if it is a series, then you know the sequence is basically the partial sum. So if the partial sum is bounded, the sequence of partial sum is bounded, then the series is convergent. Right? So here all you need to do is to just to make sure that the sequence of partial sum is monotone. If you do that, then you can clearly say that it is convergent, right? So that is not a big deal here, right? So that is why we gave this part extra, right? The terms UNs are not zero for all n, right? So that is very important here to prove the monotonicity, right? Because of that, you can see that the okay, so this is something we learn in chapter 2, right? If the sequence is monotonically increasing, right, or decreasing, right, the sequence is convergent if and only if bounded. That is something we learn, right? But now if you look at the sequence is sum of UKs. UK is equal to, so K is running from 1 to n. So if you take S1, it is U1. S2 is U1 plus U2. So S2 is obviously bigger than that, right? So because of the fact that UN is non-zero for all n, right? So then it is increasing, right? So the sequence is an increasing, monotonically increasing sequence. So if it is increasing, then it is convergent if and only if bounded. But you already know series is convergent if and only if this. Right? But you all know the series is convergent if and only if the associated, right? So the series is convergent if and only if the associated sequence is convergent, right? But you know sequence is convergent if and only if it is bounded. So if you combine both of them, right, this is convergent if and only if Sn is bounded. So if it is bounded. Right, so this is the third kind of convergent results we see in sequences, right? So the so basically, you know, in sequences you have three results. One is monotone convergence theorem, other one is Koshi sequence, right? And then you have the regular limit, right? So for all three results, you have an equivalent condition for the series as well, right? So if the series, the terms are non-zero, then the series converges if and only if the partial sum is bounded, and also the series converges if and only if it is Cauchy, and also the series converges, then the last term un goes to 0 as n goes to infinity, right? So that is how you prove the results, right? So in the next class, we are going to talk about some kind of a sub-series, right? So we call it P series, right? So that we will talk about that in the Tuesday class, right? Okay, so here are the answers for your question you asked in the chat. One is yes, we will ask to prove some of the theorems in the exams as well. So you should know how to prove the theorems, right? Especially the very important theorems like Koshi criterion and monotone convergence theorem and things like that, right? So if I prove a theorem in the class, then theorem, the proof probably will be asked in the exams as well. Or we can ask similar type of proofs, right? So instead of giving you exactly the same question, we might change the question little bit and then ask you to prove in the same way, right? So the proofs are important. You should know how to write the proof, right? And the other question why I gave 1 upon 4 is, right, because I know I want to get a contradiction here, right? The question is I want to show this one is divergent, right? So if I want to show this one is divergent, I need to show that this is not Koshi. If I want to show this is not Koshi, then I assume this is less than epsilon and get a contradiction, right? So I can choose epsilon as anything, right? So then I choose this as 1/4 so that I get 1/2 less than 1/4 at the end, right? You could have choose this as 1 upon 8 or you can choose this as 1 upon 5. Anything you can choose, right? As long as that is not less than, or that is as long as it is not greater than 1/2, right? Whatever you get here should be bigger than what you put here, right? So that is the idea here, right? Yeah, we will give you tutorial class depending on the time, right? So we will continue the classes until the end of the semester, right? So we still don't know whether the final exam will be held on time or not, right? And we don't know whether you will be allowed to come to the university or not, right? So we will continue tutorial classes as well. First, we will try to finish the syllabus, and then we will work on the tutorial so that you can have understood, you can have the understanding of all the chapters before doing the tutorial. So hopefully Kajan will post the second tutorial on the LMS today or tomorrow, right? And then he will post the other tutorials as well, right? So he will continue, he will do the tutorial class at some point of the time. So we will stop here and then we will continue the rest on the Tuesday class. Yeah, this chapter tute we are not prepared yet, so we will prepare this and put it on the LMS. We will put the tutorial for chapter 1 and chapter 2 now.